I'm Rajat. I'm going to be talking about capacity and delay scaling for broadcast in large-scale wireless networks. This is my joint work with my advisors, Sartaj Karman and Itan Modiano. So I'll start off with some motivation and then go to system model, give some related works in literature, and then go to my main contributions in this work, and end with some pointers to some future work. So what is broadcast? Broadcast is a network operation where a message has to be delivered to all other nodes in the network. And all-to-all broadcast is an operation in which all nodes are broadcasting, are sending messages to every other node in the network. So where vehicles are interested in disseminating information about congestion or a traffic collision to other vehicles. In a futuristic multi-UAV network, UAVs are interested in disseminating information about position, velocity, and other control information for safety and collision avoidance. So, what are the main limiting factors? The three: one is wireless interference, second is growing network size, and third is high mobility. So, wireless interference essentially limits the number of simultaneous transmissions. So, for example, in this figure, the red link and blue link cannot transmit simultaneously due to interference. With diminishing size of radios, you have high density of nodes. So that's another factor that we have to deal with in designing the systems. Third is high mobility. So classical applications of wireless, moving from cellular to vehicular to maybe multi-UAV systems in the future, you see an increasing trend in mobility. So that is, and high mobility will make connectivity between nodes intermittent. So that is another factor, that limiting factor that needs to be countered while designing broadcast or any wireless network operation. So here's motivated by this, here's my system model. My time is slotted. I have a unit square or a torus to be precise. Mobility works as follows. A node starts at X, chooses a location Y uniformly randomly in this space and moves to it. Because the transmission radius is limited, we model this using a cell partition structure. So I divide my entire space into C cells, and the size of each cell sort of represents the coverage area of transmission. So the interference model is only one successful transmission can happen in a given cell, and there's no cross-cell interference. To model high mobility, I assume that node reaches its destination Y right at the beginning of the next slot. And so I'm interested in broadcast. So I have Poisson arrival rate lambda at each node, and it has to broadcast this message to all other nodes in the network. And how does so I have n nodes, and I'm interested in capacity and delay as n scales to infinity. So how does capacity and delay scale? And by delay, I mean it's the time required for a packet from arrival till the time it reaches all nodes. So before I move to related literature, I want to make a point on cell sizes. So when you're doing broadcast, choosing a right cell size might help. This is because the wireless medium is broadcast by nature. So if I have a larger cell size, one transmission in a cell can reach many nodes, but this comes at a cost of fewer simultaneous transmissions because of interference. So what I do is we'll pick a cell size C to be n power alpha. Actually, the results hold for any general cell size, but this is for simplicity of presentation. So I have C cells, which is n power alpha, which means the size or area of each cell is 1 over C, because the total area is 1, which is given by n power minus alpha. So the average node density, which is n, total number of nodes, divided by C, number of cells, is n power 1 minus alpha. Now I'll make two categories. One is sparse network, where the node density does not scale in n or does not increase in n, and dense network where the node density increases in. So the dense case is alpha between 0 and 1, and the sparse case is when alpha is greater than or equal to 1. So now This sort of mobility model was first studied by Neely and Modiano in 2005, but the focus was on unicast. So they had n nodes, of which n by 2 were source nodes and n by 2 were destination nodes. We had n by 2 source destination pairs, and what was studied, and the number of cells were proportional to n, and what was observed was that, or rather proved was that you had a capacity delay trade-off, which looked as follows. So here I have plotted delay scalings and capacity. So you could achieve order 1 capacity or throughput, but that came at a delay of order n. You could get a better delay, but that had to come at a price of lowering your throughput. Now, similar results were obtained for unicast case for more general mobility models like Markov, random waypoint, and similar trade-offs were observed. And in 2011, multicast was studied, where a source had several destinations, and as a side, a capacity delay trade-off was speculated for broadcast. In this work, we proved that there's nearly no such trade-off. That is, you have a maximum capacity, minimum delay, and a scheme that nearly achieves minimum delay and maximum capacity. So the outline of my talk, I'll first discuss the bounds. I'll have a capacity bound and minimum delay, and then I'll move to a proposed scheme, which I call FCFS flooding scheme, first come first serve flooding scheme, and analyze this using what are called Markov evolving graphs and flooding time. So the first capacity result, so this says that any achievable rate lambda is upper bounded by this quantity. So I plot this here. In fact, this upper bound is achievable, and I won't go through the proof, but here's how it looks like. So this y-axis is capacity, and this is alpha. Alpha is related to the cell size. So increasing cell size is in this direction. So what this result says is, as my cell increases, my capacity increases in terms of scaling, but not beyond a point. And that point is alpha a number of cells proportional to n. So my density is constant at this point. Okay, there you go. So this is capacity, this is minimum delay. So the second result is a lower bound on minimum delay. So the minimum achievable delay is given by this quantity for the sparse and dense case. So here I plot lower bound on delay given by this expression and alpha. So as my cell size increases, my delay reduces, but again not beyond a point, and that point is again C proportional to n, or constant density. How do I prove this? So the proof is really simple. Consider a single packet using all resources. A single packet starts from one node and uses the entire all the network resources, and the time it takes to reach that single packet takes to reach all nodes, I'll call it flooding time. Then this flooding time will be a lower bound on the delay that I can achieve for any scheme. So a lower bound on this flooding time will give me a lower bound on delay. So in the last theorem, that is this derived thing is the lower bound on this flooding time. The interesting that I show next is that an upper bound on this flooding time is in fact achievable. And so what this means is, to prove minimum delay achievability, I need to obtain accurate bounds on this flooding time. That is what I'll obtain in the subsequent slides. Now to demonstrate achievability, we propose this FCFS flooding scheme. And here's how the flooding scheme works. So packet arrive at all nodes. The packet that arrived earliest in time gets service. And so it's almost like you run a single packet flooding scheme on the earliest arrived packet. Now suppose I have, I'll do a slight variation of this. Suppose I have an upper bound un on the flooding time. Then I'll run the single packet flooding scheme in this procedure for a bounded time of un. Then the entire network becomes a single queue where you have all the n arrivals. So you have n lambda because you have lambda arrivals at each node. So you have total arrival of n lambda and a deterministic service of time un, because un is an upper bound on flooding time. Now, the waiting time in this queue for a packet is the average waiting time for the FCFS flooding scheme. And that we know from MD1 queue expression analysis. And that is of order UN if rho is set to constant. So what happens is, if UN is an upper bound on flooding time, then I can achieve that much delay for using my FCFS flooding scheme at this throughput. We also see that, so next I'll get so I haven't yet given you an upper bound, but next I get an upper bound, and when I get a tight upper bound, it so happens that this lambda turns out to be the maximum capacity. So how do I get flooding time bounds? So let me describe flooding time for a static graph, and then I'll move to a flooding time for a random graph. So I have a graph with n nodes, and so initially only one node has packet, so the red node has the packet. So in the next time slot, all its neighbors will have the packet. In the time slot after that, all their neighbors will have the packet, and so on till the entire network gets the packet. And the time it requires to do this is flooding. So what I'll and let n of I be the nodes that will get the packet in the next time slot. So here's a result. So if I have, and this is by Clementi in 2011, it says that if I have some sequence of thresholds going from 1 to n by 2, n is the total number of nodes, such that the total number of nodes, that the set of nodes that have packet is of size between these two thresholds, then the number of new nodes that will get that packet is at least a factor ki times size of I. And this holds for all these thresholds. So essentially, if you are able to find such thresholds that satisfy this property, which is called expander property, then you have a bound on flooding time given by this, which is a log of ratio of two consecutive thresholds divided by log of the factor in which it expands. Now, this is for deterministic graph, but it so happens that it holds for randomly evolving graphs, namely Markov evolving graphs. Now, what are Markov evolving graphs? Markov evolving graphs is a Markov chain over state space, which is a set of graphs over finite set n nodes. So our network model is naturally a Markov evolving graph. Actually, it's an IID evolving graph. So if I just connect join edges between two nodes that are in the same cell, then our network becomes a Markov evolving graphs, and we can use Clementi's result. But here's the Clementi's result for Markov evolving graphs. So the previous one was for deterministic graph. So when you have a Markov evolving graph, what the extension of it is, if the expander property is satisfied with high probability, then the same flooding time bound holds with high probability. But there's a catch, and that is this expander property is not always satisfied. So when our network is dense, then that is the average number of nodes in a cell increases in n, then this expander property is satisfied with high probability. But when it is sparse, that is the number of nodes in a cell is constant or decreasing in n, then this expander property is not satisfied. So we can't use this bound. So what we do is we extend this bound using a very simple, another simple bound. So here's the result. So if I are set of infected nodes, the cardinality of I is h. If I can lower bound the probability that one more node will get the message by ph, then the flooding time is upper bounded by this quantity. This is essentially bounding flooding time by sum of geometric random variables. So you think as if the flooding happens by infecting one node at a time. So this doesn't use any expander property at all. But we can combine the two ideas, because most often what happens is, initially when the packet starts with just one node, it expands slowly with one node at a time, and after it reaches a certain population, it starts behaving by satisfying the expander property. So if the expander property is partially satisfied, after a certain threshold of population, then the following bound holds for flooding time. Now we use these three bounds to prove to get an upper bound on flooding time. So the black line is the lower bound on flooding time, which is also the minimum delay that we obtain in the minimum delay result, and this the red line is the upper bound on flooding time. So we see in the sparse case the two coincide in terms of scaling, and there's a log n gap in the dense case scenario. So no. So for Markov evolving graphs, the expander property has to hold, but it is not always the case. It may partially hold in the sense that once a certain population of nodes have the packet, then from then onwards the expander property may hold, but not before that. And before that, the flooding might take place with just infecting one node at a time, and once it reaches a certain population, it will expand in a multiplicative fashion. So in that case, this result holds, but yes, and that's why here the H1, that threshold, this H1 characterizes what fraction of population needs to be infected, whereas in Clementi's case, this H1 had to be equal to 1. It had to hold right from beginning. So we get tight bound. So tight bound means okay. So this is a summary of results. So here I plot for the sparse case and dense case. This is delay, and this is capacity, delay and capacity. So this is the maximum capacity that we got from first result. It's the lower bound on delay, and the FCFS flooding scheme achieves minimum delay in this case, but is factor log n away from the maximum capacity, from the capacity. Here it is factor log n away from both delay and capacity. We think, so this gap of log n is due to the gap between flooding time bound, upper and lower bound. And here, I haven't proved this, but I think the gap is because I'm assuming I'm allowing only one packet which arrived the earliest to get priority over the network. So this shows that there's nearly no trade-off between capacity and delay, as was speculated earlier. Okay, so to conclude, so we analyzed broadcast in mobile wireless networks as number of nodes scaled to infinity. We essentially got capacity and minimum delay scalings. We saw that increasing set sizes improves capacity and lowers minimum delay. But there was no gain beyond a point. We showed that a simple FCFS flooding scheme nearly achieves capacity and delays. So there's no capacity delay trade-off. And we used Markov evolving graphs to get these bounds, which are not possible before. So as a pointer to future work, it would be interesting to analyze this for random waypoint, Markov and Brownian motion, because of more practicality, especially the random waypoint. And I think multicast is still an open problem, which nobody has addressed. Thank you.